Well, I'm going to talk about, I think, a wide variety of things, hopefully in a sequence that makes sense. So first, let me tell you a little bit about me in that I have, well, I'm a magnetic fusion guy. I've been doing magnetic fusion for 50 years, so I don't know why you invite people who have not been successful in achieving magnetic fusion. But anyway, we have been working at it, and we like to believe, and are, I will try to convince you, making progress. However, it's still long, still much to go. As for the particulars, at the University of Wisconsin-Madison, I am an emeritus professor for over 10 years now, but in the United States, you can still continue on, have research grants from the Department of Energy, United States government, and you can continue on. So old professors fade away, but somewhat slow, let's say, and depends on the person, of course. So anyway, this sequence of lectures, I am after trying to tell you about what goes into obtaining the equations we try to solve and the particular equations going from very short time scales, microscopic, through intermediate time scales where collisions become important, fluid moment time scales, MHD, extended MHD, and finally, very long time scales, transport time scales, as we call it, because I'm going to mainly talk about magnetic fusion with only a little bit about inertial confinement, in that the equations that I mentioned without magnetic field will be possibly relevant to magnetic inertial confinement. So today, what I want to tell you about is how do Coulomb collisions affect charged particle motion. This is important, I think, because there's a difference between how charged particles move in a plasma as compared to what we do with a Boltzmann collision operator for neutral particle collisions. So then I want to tell you about what are the collision operators and the plasma kinetic equation that we will use, and that are used throughout a large fraction of plasma physics, not just magnetic fusion. And then a little bit about what procedures, various types of procedures that are used to solve the plasma kinetic equation, but then future lectures will be more on the details of that. So as a background, a little bit inertial confinement magnetic, and as emphasized by the speakers this morning, a lot of the magnetic fusion effort is focused on moving towards ether, and I'll want to mention the parameters of that. Then I'll tell you about Coulomb collisional scattering of a charged particle. It mainly affects its velocity. We'll talk about that. Then the comprehensive plasma kinetic equation that is more or less valid for everything in magnetic fusion. And then a Fokker-Planck, and then adaptations later. The Fokker-Planck collision operator, which is again very general. And then how one solves this somewhat in collisional, and I'll tell you about a perhaps new technique, Green's function, in 6-dimensional phase space. So, as some of the speakers this morning have mentioned, plasma physics is a young field, only 50 years or so, but it's a combination of mechanics, electricity and magnetism, statistical mechanics, kinetic theory of gases, and fluid mechanics. And at least in magnetic fusion, relativity is not so important because the temperatures we'll talk about are 10 kilovolts, 20 kilovolts. The rest mass energy of an electron is 511 kilovolts. There are some special applications, but I will try to get the most basic parts of the theory. And also, quantum mechanics is not important because our length scales will be longer than de Broglie wavelengths for the most part. One exception I'll mention later. So what distinguishes, and we will be talking about fully ionized plasmas. There may be some neutrals coming in from the edge, but in the most of the plasma, neutrals are totally unimportant. And so it's a fully ionized plasma. And as emphasized by Professor Rax, the Coulomb collision interaction potentials, both speakers actually, are much smaller than the thermal energies. And the charge particle interactions then are collective, many together, to give you Debye shielding, as we'll talk about, not individual particle collisions. And these collective interactions have many interesting physical consequences. Namely, we'll talk about, they of course, Debye shield charges. Professor Rax presented some of that. We'll talk some more about it. The collective interactions can, like in Landau damping, transfer organized information of a wave you put into the particle distribution function. And so it's a transfer from waves to particles. And then you can have the opposite, an instability, where you transfer energy from the particles, like a laser, a beam or something, back into the waves, or from the waves back into collective instabilities, or into particles back into collective. And so unlike fluid mechanics, which has only 3 dimensions, in plasma physics we often have to deal with all 6 phase space dimensions, although pragmatically in magnetic fusion we will average over gyro motion, so we'll only have 5 dimensions really to deal with. The overriding objective that's pushed much of plasma physics research, and certainly the funding, has been provided primarily for a fusion energy objective. And that can be somewhat, you want to have deuterons and tritons colliding, producing about 17 MeV, 14 MeV neutron, 3.5 MeV alpha particle, helium nucleus. And so in order to overcome their Coulomb repulsion, you have to have more than about 4.5, 5 kilovolt energy. And roughly speaking, if you could have a plasma with 10 kilovolts, you could get some good fusion reactions. So we need about an ion temperature of deuterium tritium, about 10 kilovolts. And we need to confine it for long enough time for enough fusion reactions to happen. And that requires a time greater than about 310 to the 20th divided by the ion or deuteron density, units of seconds. So in inertial fusion, what you take is a 1 centimeter or less capsule, and you compress that to a density of almost 10 to the 28th per cubic meter. These are very rough numbers, by the way. And you do that as Professor, I can't pronounce it. How do you pronounce your name? Sorry, Tikhonchuk. Anyway, 60 nanoseconds or so, okay? You try to compress. Magnetic fusion is the opposite way. You use a magnetic field of about 5 Tesla in a toroidal configuration we'll talk about. You try to combine densities of order 10 to the 20th per cubic meter, and you try to hold it for 6 seconds, 3, 4, 5, 6 seconds. Tau sub e will be, you put in energy, heating processes, how long does it take to escape? It's the same as if I were to calculate the heat flow through the wall. How long, when I put heat in here, does it take for that heat to disappear? And we're trying to hold this high temperature plasma for about 6 seconds. So, of course, this you saw earlier this morning, but I will emphasize some additional aspects. So the next step in tokamak magnetic fusion research, and as indicated in previous slides, the tokamak is the leading magnetic confinement configuration. And I first started working on a device which was about this big across, you know, or working on the theories having to do. Things have gotten a little larger over the years. Here's a standard, presumably slightly less than 2-meter man or woman. No, it's a man in this case. But you can see this is a very large device, okay? And it is, of course, being built up in Cadarache by a consortium of which the European Union is providing 45% of the funding, and each of the other partners 9% each. You have to figure out the detailed numbers. The major radius, which is the distance from this symmetry axis here out to the midplane, the midpoint of this torus of a donut, the center of the donut, is about 6 meters. The minor radius from there to there of a cylindrical system, sort of, is 2 meters, and the height's 3.5, 4 average. Toroidal field maybe 5.6 Tesla. We will try to inductively drive a current around inside the donut of about 15 megamps. Heating power will be supplied by some of these various little things like this: energetic neutral beams, radio frequency waves, microwaves, etc. The projections are first plasma 2020. It has a question mark behind it because there's continual funding questions and timing questions and all kinds of things. And then DT, that will only be first plasma, not of a fusion nature, but of a demonstration that it's sort of working. And then DT fusion in 2027. And it's supposed to try to get fusion energy, not on the grid, but fusion energy out of the system compared to the heating power going in of a factor of 10. The experiments in TFTR in the United States and JET and in Coulomb, England, Europe, achieved about Q of about 0.3. Many politicians say, will this actually work? And we're hoping to show yes. But from the scientific community, people generally believe that the already achievement of Q of about 0.3 demonstrates more or less the scientific feasibility of fusion. Depending on which side of this coin you're on, it's really yet to be demonstrated or not. That's an open question. But obviously this experiment is, let's make sure we can get there, is the idea. And a total fusion power out of 500 megawatts. However, I should point out that of that 500 megawatts, 400 will be coming out in 14 MeV neutrons, and about 100 into the plasma, roughly speaking, to reheat it so you can take away the external power to some degree. Okay, now, whoops, sorry. Now, I happen to, while I'm at the University of Wisconsin, have a collaborative agreement. You may know that the University of Wisconsin is in the north of the United States and has a climate very similar to Moscow. We've had some Soviet visitors. And so I have to go collaborate with people at General Atomics in San Diego, like Javier did some years ago. And I go in February for a couple-week visit for good reason, obviously. Anyway, so I collaborate on this experiment present experiment in the United States, which is the leading one in the United States. It is a little smaller dimension. So here's 1 meter. A 2 meter person would be double this size, right? And so this is the parameters of that device, more like 1.7 meters, 0.7 meters, 2.4 Tesla, so forth. Some of the things they've accomplished, a big measure in magnetic fusion is how much pressure can I hold relative to the magnetic energy density. Obviously, if I had too much pressure, I would overwhelm, push past the magnetic field, which is what you do in solar wind and things like that. But if I really want to confine the plasma, I need to have a pressure less than the magnetic energy density. And so they've achieved that. They've achieved control of things like what I'll call neoclassical tearing modes will come away, which are intermediate scale resistive or neoclassical MHD instabilities, which are we'll talk a little bit about later. And they've also been using a lot recently of control of the plasma flow, toroidal flow particularly, with non-axisymmetric extra fields. I should have said, and we'll come back to this, the tokamak is nearly axisymmetric. Means, you know, the symmetry axis is here, and if I go around, everything's more or less constant. We apply extra fields in the units of about 10 to the minus 3, 10 to the minus 4. So small perturbations on type of axisymmetry. So our description will be able to be two-dimensional, or what we sometimes call 1.5 dimensional, which is, and we'll talk about how we get these, magnetic flux surfaces here, which are then surfaces around like this all the way, and magnetic field lines are going helically around those surfaces, but to lowest order, the plasma is held on those surfaces, and what we will care about in a long time is then how fast plasma leaks, diffuses, roughly speaking, across those fields. Then we also have other things they've done more recently about controlling edge instabilities. Now, particularly in plasma physics, we have, and in magnetic fusion certainly, and also inertial, we have various time scales, and there are various different processes on different time scales. So what I'd like to try to illustrate is some of those time scales for ITER. This is, of course, a device to be built. So it's not operating yet, but this is to give you a feeling for where are we trying to go. So the projected parameters are toroidal field of 4.6 Tesla, temperatures of deuterons and tritons and electrons of 10 kilovolts, an electron density of 10 to the 20th per meter cubed, and a major to minor radius of 6 to 2 meters. Now, there are then many different time scales and many different length scales. And my basic point is we have to go from very microscopic dimensions, de Broglie wavelengths, quantum mechanical de Broglie wavelengths of the order of 10 to the minus 12th meters, up to collision lengths, which are going to be 12 kilometers. Okay, that's a long spatial scale. But I like to more characterize all this in terms of time scales. So the plasma period, which is just if you shake a plasma, what frequency does it like to shake at on the microscopic level, answers the plasma frequency. And so you can write a plasma period, 1 over that frequency. It's a picosecond, okay? Very short time scale. Then we're going to have a strong magnetic field, and we're going to have ions gyrating around it. The frequency of that gyrating is known as the gyro period, or at the cyclotron frequency. That might be 3 nanoseconds. Then if we have Alfvén waves in the plasma, they may be sub-microsecond, or a little longer maybe. Electron collision times we're going to talk about is about 200 microseconds or 0.2 milliseconds. The deuteron collision time is another couple orders of magnitude longer, 30 milliseconds. The energy confinement time we need to achieve to hold the plasma long enough to get enough fusion is, for ITER, let's say 6 seconds. And the fusion collision time, actually, fusion collisions are very infrequent compared to just scattering, Coulomb scattering collisions by a factor of 60, okay? So, or what have I got here? 6 into 200, so 30 or something like that. So anyway, now how long, so if we're going to develop a theory of how ITER confines plasmas, in principle, we have to deal with all of these shorter timescales out to the collision time, out to the fusion time. Really, at least we've got to deal with to the energy confinement timescale. So anyway, then there's a set of dimensionless parameters I want to mention here. So, as Professor Vrax was indicating, and Tkaczyk as well, we have a parameter number of particles in a Debye sphere, and I'll come back to that. And it's effectively a parameter that characterizes, if it's very large, it means you have a large thermal energy compared to the Coulomb interaction potential at, roughly speaking, say, the interparticle distance. So as long as we have many particles in a Debye sphere, we have a weakly coupled medium, or a collective medium, or a polarizable medium, however you want to talk about it. ICF tends to have, I just wrote those numbers down here. I had the preceding numbers for the sort of, you know, small pellets and stuff and densities. Anyway, magnetic fusion tends to have 10 to the 7th or more for this number of electrons in a Debye cube, and I'll come back to that over here. Then it turns out that the collision rate, electron collision rates, which we'll derive some in detail so you get a feeling for it, is 1 over that parameter of the plasma frequency. So the plasma frequency was the natural shaking at short Debye length scales. But roughly speaking, the collision frequency, net collision frequency, is down by 8 orders of magnitude in ITER, only about 5 orders of magnitude, from that natural shaking frequency. And another key parameter in tokamaks is if my, you know, this is the minor radius of ITER, that's about right, 2 meters. How big is the gyro radius? You know, the ions are going to go along the field line and they're going to have a gyro radius. Well, it turns out it's about 3 millimeters, okay? So roughly speaking, we're going to have about 1,000, well, and the average radius of the plasma, because it's taller than it is in the midplane, roughly speaking, we got 1,000 gyro radii across the plasma. We characterize that by a parameter called rho star, which is the ratio of the deuteron gyro radius to the average radius of the plasma. Now, as we'll come back to many times, and was mentioned earlier this morning, there are these so-called Brzezinski collisional plasma equations, and we'll want to talk a lot about those because they're a good set of fluid-type equations to describe a magnetically confined plasma. They have as an approximation that the collision length is short compared to the gradient scale lengths. Well, in tokamaks, okay, the collision length over the, say, toroidal circumference, 2 pi r, is 320. So we've got 320 transits in one collision time. this is not a high collisionality plasma. So, you know, the Brzezinski equations will not directly apply. However, I will want to tell you about how we can patch it up, and in part, in various ways. In contrast, in ICF, I got a number like 0.4. You mentioned it's of order unity. And it depends, you're so inhomogeneous that, that you go from, and the energetic particles are more collisionless than this. You're in the worst regime, not low, not high, but right there in the middle. So anyway, this is to give you a feel for some of these numbers. And I wrote them kind of on this board over here, which I'll leave for you, which again just says the time in seconds. And we want to go all the way out here, okay? The plasma's out here, and we've got to get through, in some sense, all these time scales to get a description of a tokamak plasma. Okay, so next I just want to say, so the device, like I say, I collaborate with the folks at General Atomics on. They're only at 2 Tesla, 3 kilovolts, 310 to the 19th. Z effective, they always have a little bit of carbon impurities and stuff. About 2, and they're about 1.7 meter, 0.7. And all I want to say in this graph is that their numbers, these dimensionless numbers, are not that much different than ITER. The big differences are basically that instead of 1,000 gyroradii across the plasma, they're more like 160 gyroradii across gyroradii. But it's a small parameter. We think we're sort of okay. But there's a big question of how this will scale, how in particular the so-called transport across the field lines will scale. Okay, so I'm forgetting. So modeling tokamaks from these very short time scales all the way out to the transport energy confinement time scales will involve some very important approximations. The most fundamental is perhaps that this is small gyro radius approximation, small gyro radius compared to the minor radius. And we're going to have physically, along magnetic field lines, particles that are almost free streaming. So the magnetic field is this helical magnetic field that we'll come back to later. And particles go from the inboard side of the tokamak to the outboard and back. And so that's free streaming, so to speak. But then it turns out they'll drift off a little bit from the field, from the individual magnetic field lines. And we might get some magnetic reconnection. It's not a perfect magnetic field with no resistivity. There's some resistivity, and that will cause some reconnection at rational surfaces where field lines close back on themselves. And then what we have to care about is gyroradii colliding gives you some transport, drift, what are called banana orbits, drift orbits that are more physically larger, and they will cause diffusion. And then we have turbulence. I would like to, however, emphasize, for the most part, the turbulence we have in tokamaks, if the plasma is this big, well, in D3D it's about this big, it turns out that there are fluctuations in the plasma, but unlike hydrodynamics, where you have a big eddy that's all the way from the core to the wall if you have flow down a pipe, in tokamaks, for the most part, you get just local cells, and those cells may be 5 or 10 times in width the gyroradii. But if we have 160 gyroradii 10 times, you know, you still got a number of eddy scale length sizes in the device. This is sort of true except at the very edge of a tokamak in a similar sense to viscous hydrodynamics, that you have an edge layer. if you're going to have a heat flow come out of the tokamak, you put in a lot of heat in the center, it diffuses out. Out towards the edge, these local microscopic turbulence instabilities and stuff tend to not be able to carry enough power. They're little weak things. And so I think you're going to mention these are one of these examples where things don't quite work. And Javier are going to talk Wednesday, I believe. So I'm going to tell you all the things that I'd hope would work, and he's going to tell you some things that make it so it doesn't work in certain regimes from what I read in the abstract. Is that fair? So I'm trying to tell you the straight story, and he'll give you the complication, or no, it doesn't quite work. And I am not going to talk about those micro instabilities. What I'm going to talk about is try to give you a framework that fits those micro instabilities and many other things all in one framework. So now what I want to emphasize, however, is that Coulomb collisions are actually very important on many timescales. When timescales are much less than the collision times, then actually they're not too important, except I'm going to tell you at the beginning of next lecture about collisional effects on lambda damping, where actually if you have resonant phenomena, then Coulomb collisions do matter because they give you singular layers, boundary layers that scale like fractional powers of the collision frequency, and there collisions can become important. But in general, on short time scales, you don't have too much collisional effects. Then, for time scales longer than collision times, the collisions force the distribution function into a Maxwellian. And then you can use a fluid moment description, and your job, so to speak, becomes to calculate proper closure relations to use those fluid equations with closures that are consistent, and I'll get into that quite a bit. And then finally, in energy confinement timescales, you're in a random walk situation, and so your length scale is maybe the minor radius, and there's maybe a collision frequency or a decorrelation rate, for instance, eddy decorrelation rate or something, and you have to worry about all the cross-field across these surfaces transport. But I will actually talk more about 3D field effects, as you'll see why in some time. Okay, the next is a bit of a side comment, okay? So the emphasis in physics, and plasma physics certainly, is on identifying the relevant physical processes involved and what key physical processes must be included for understanding some particular phenomena, and then what reduced mathematical description can we use to describe them, and then always truthfully what length and time scales are involved for any one description. One description be ideal MHD, another would be Brzezinski equations, another would be net transport equations for a tokamak. Everything we do in plasma physics is a set of approximations, okay? Now, so you have to say, well, they're only only approximate representations of the real physical systems. By the way, you could say, well, look, I can surely with a big computer, do all this. But it turns out in ITER, there are on the order of 10 to the 23 particles, charged particles in that device. If you imagined I tried to follow them on a computer, 10 to the 23rd particles, I just follow their orbits or their trajectories. It's a little, you might get a nanosecond or so that you could begin to follow. There's no way you can go out to seconds and stuff like that. So we have reduced models. And we have many small expansion parameters, and often they're very small, and even fractional powers of them are involved in singular layer phenomena, resolving resonances, resonance broadening it's sometimes called. And you can get key additional physics. If you reconnect field lines, you can create island topologies within the torus. It's not those nice nested flux surfaces, but it actually has magnetic islands in it. So in exploring mathematical properties of equations and developing numerical algorithms, be aware of the parameter regime limits and don't violate them. We should have Courant conditions for various elements of plasma physics. Now, however, I might say that most of my numerical friends will ask me, well, what exactly are your approximations, or what's the limits? Well, it's kind of this way. I would have to say the physics community, plasma physics community, at least in fusion, magnetic fusion, is not terribly good about quantifying, maybe you're good in inertial, I don't know, about quantifying, well, how far can I push this model, or something like that. But be aware that there are these limits on any one, and I'll come back to some particular ones. As an example, I will just mention, we will talk about the Vlasov equation, which says neglect collisions. Well, that has some ramifications, and I think we need to be more aware of those ramifications. So anyway, this is just a caution. Try to figure out what it is, or the Courant conditions, the limiting conditions that need to be satisfied for various physics models. So we have on tokamaks a number of things we have to worry about. It involves a hierarchy of timescales. So we've got this much less than the collision time, electron collision time. And the ions, basically electrons are 3,672 times lower mass. And so at the same temperature, they're moving square root of that 60 times faster than ions. And so they're the fastest. An old professor that I had said, the electrons have long arms when they're swimming. The ions are big and slow. So they're different by a factor of 60, okay? So very different time scales. Then on the collisional time scale, on about the 200 microseconds again for ITER, we end up developing an appropriate Ohm's law, an electron distribution that's more or less Maxwellian, and we have a real meaningful Ohm's law. However, in addition, we'll have that the ion poloidal flow around the short way around the tokamak will get damped by ion collision times, and we need to have these things come up. And then ideal MHD is applicable on this collisionless time scale, but with dissipated processes like Ohm's law resistivity, and actually some viscosity there as well we'll talk about. You can get new types of instabilities beyond the ideal MHD instabilities. These instabilities are more like what we call resistive MHD instabilities and neoclassical MHD, which I'll sort of explain later. And they allow reconnection of magnetic field lines on rational surfaces, meaning surfaces where a field line goes around the torus and bites its tail, so it's vulnerable to small perturbations. The present jargon, at least in the United States, is that the maybe grand challenge in fusion, let me call it theoretical and applied math research, is to develop a predictive capability for plasma behavior in present tokamaks and in ITER. And it appears that we will have to do that by a combination of sort of kinetic models, ideal MHD, extended MHD, and transport. So it's a hierarchy of models. And I personally regard the collision stuff as very important. Other people work on other things. And so I want to tell you a lot in these lectures about collision effects. So pedagogically, I'll begin with a microscopic description of those Coulomb collisional interactions. And this determines the trajectories of electron and ion charged particles in the plasma. And then we will develop a Fokker-Planck collision operator that embodies these effects. And then this will allow us to produce a plasma kinetic equation that includes this collision operator. And then finally, we will discuss the properties and methods of how we solve that equation in a sort of generic sense. Now this is a diagram reproduced over here a little bit. When you study neutral gases, you think of gas in this room and you ask, I have a neutral here of a certain whatever, well, not hydrogen, we wouldn't want that, but say a nitrogen molecule, and it moves along straight lines, and then it suffers a collision, and it more or less goes in a random direction afterwards. So I've indicated that on the left. That is to say, a neutral comes along, hits another, maybe another neutral, and goes in a straight line, hits a, say, ion, and then goes up, okay? And we talk about a mean-free path between collisions. For charged particles in a plasma, that's not the right way to think about things. So as we start out here, this electron went on this orbit here, trajectory, went past a neutral, it didn't even notice it because there was no force field. Didn't get so close. On the other hand, it gets a little bit close to that ion, so it, electron going past an ion twists a little bit, or deflects, or scatters. And then it goes over here and went past another one, and then arcs back that way. So a charged particle in a magnetized plasma, and these any weak coupled plasma, is actually doing this. And so its velocity vector is scattering, okay? And so then it's not really appropriate to talk about a collision length because, I had 10 collisions in going across here, 10 strong collisions, and actually every one of these charged particles has a Coulomb potential around it, and it's scattering me. Oh my gosh. So every particle in the plasma is coupled. No, we'll have Debye shielding that'll cut that off, thank goodness, okay? But anyway, I'm suffering a lot of collisions as I move through. So what do we talk about? Well, eventually the particle was going this way, and it was going this way and finally goes that way. So, he scattered through 90 degrees. So roughly speaking, that's what we'll characterize as a collision frequency or rate. And the collision length will be the length over which I lose my directed momentum. But that's a very different physical process. This will, of course, lead to a Boltzmann collision operator. This will lead to a Fokker-Planck velocity space scattering operator, a diffusion operator in velocity space. So, but luckily, rather than all 10 to the 23rd particles being, coupled together, there's something called Debye shielding. So if you introduce a single particle here, and I'll make use of this word quite often, a test particle in the plasma, it creates a Coulomb potential around it. And in doing so, it causes all these other particles to feel it. And so the density of those other particles will obey a Boltzmann relation. So it's a density of the other particles will be the equilibrium density times e to the minus q of that particle times the test particle potential, which, you know, was caused by that the Coulomb potential. Well, so you just linearize that, and you can check it posteriori. Put it into Poisson's equation, and you have the charge density caused by the test particle plus this polarization charge that this particle causes the other particles to respond a little bit, and you end up with this equation for the test particle potential around the potential around that test particle. And lo and behold, of course, the solution of this is just the Coulomb potential, qt over 4 pi epsilon naught. I write that in squigglies to sort of say that's a funny symbol that has to do specifically with MKS units. But anyway, so it's q over the distance of separation, the potential, and that would give an electric field, minus grad phi, that falls off like 1 over x squared. But lo and behold, the fact that I had the medium was polarizable, I get Debye shielding on some sort of scale. Debye shielding for our plasmas is going to be about 10 to the minus 4 meters. Okay? So, you know, I'm this big and I can't even see it, but anyway. And then the question becomes how many particles, as I'm moving in about a plasma period, a plasma 1 over the plasma frequency, how many particles am I interacting with simultaneously? Roughly speaking, it's n lambda Debye cubed. Number of particles in a Debye cube, Debye sphere, whatever. That turns out to be about 10 to the 7th. So roughly speaking, as a particle moves through, it feels the Coulomb potentials of all of these particles out to a distance of about a Debye length. And just for other things, the B-min quantum mechanical, which is how close do I come to another particle, is given by the de Broglie wavelength, is about 10 to the minus 12 meters. How big is a Fermi for nuclear reactions? It's 10 to the minus 14, 10 to the minus 15 meters. So it's a lot smaller than that. And how far apart are particles on average? You know, they're like 10 to the minus 7 meters or so. So we got a lot of particles that we're having Coulomb interactions with, and so we actually get a statistical description very rapidly, even in crossing 1 Debye length. So then you can say, well, I'd like to know as I move along and I go kind of past one particular background or field particle, we'll call it, then the force on that electron as it moves past that field particle is given by the charge of the electron times the electric field around that other particle, and that's 1 over x squared. And so every time I go past one particular particle, I get a momentum transfer, okay, a delta V. A little momentum kick from going past any one particle. Then you have to say, but hey, I'm going past all these particles simultaneously. And when you do that and you try to integrate it up, you end up with B here is something called the impact parameter. You may have seen this. So impact parameter is how close does this electron go past that particular ion. And you have to integrate, and turns out the integral dB over B, whereas the impact distance is from 0 to infinity. Well, that's kind of a bad integral. The logarithm of infinity over 0 is not very well defined. So infinity, well, past a Debye length, the electric field dies off because of the Debye shielding process. And going close, I can't go closer than a de Broglie wavelength, it turns out. So you end up saying, well, I'll just give myself, you end up with the logarithm of the Debye length as the long distance this would be a log B over log B, you know, divided by B minimum, which will be B minimum quantum mechanical. That's what we call in the business log lambda. So this produces Fokker-Planck coefficients. Impulse, which is, however, random. Remember, I go past this particle, I get kicked that way, I go past the next one, get kicked that way, and so forth. So I'm diffusing, I'm getting a delta V, ensemble averaged. Ensemble average here is I'm an electron moving through a whole bunch of ions, and I'm, you know, getting kicked randomly by all these n lambda Debye cubed particles within a Debye sphere. So roughly speaking, what you find, you do the analysis, and we're going to talk a little bit more detail about this, is that the delta V over delta T, which is the momentum impulse per unit time, is some collision frequency times that velocity. We will end up later talking about this as dynamical friction. Because the test electron is moving through a bunch of charges, it's suffering a little bit of, you know, drag because it's of all those collisions, and it's scattering in velocity space. So what it's really doing is, if you imagine a constant energy sphere, it's scattering on that constant energy sphere its vectorial direction, but in doing so it's losing a little bit of its speed or directed momentum, really. This collision frequency is given by some formula like this, which turns out to be this plasma frequency, which is again the natural shaking frequency, divided by n lambda Debye cubed, times log lambda, but anyway. So this is 7 orders of magnitude smaller than the shaking frequency. But we need to care about it because we need to calculate out on this time scale, taking account of those net collisions, even though they're extremely weak. So now, so let me see. 13. So Coulomb collisions scatter the velocity. And so a simple model, which I've been talking about, was with scattering of light electrons with heavy immobile ions. They scatter through what we would call a pitch angle, an angle of scattering, which is V purple V and square root of nu. And so roughly speaking, this produces a probability distribution that in this model, the so-called Lorentz scattering model, I'm on a constant energy sphere because the background ions don't move. So it's a delta function in speed or energy, and then it's a probabilistic distribution, which becomes a delta function at time equals 0, but you know, spreads collisionally in angle. And then you can say, well, suppose that this is not just one electron, but it's a whole fluid of electrons that has a flow velocity, okay? And you can ask on that fluid flow velocity, what's the effective electron collision frequency? And that's this nu sub e that I refer to as 200 microseconds or so. And so then you also have, what's the fundamental momentum loss? So I had a fluid moving, and you know, over what length scale do I dissipate that momentum? And the answer then is a thermal velocity divided by that effective collision frequency. And this is just a number, but it's huge number. This is like n lambda Debye cubed, the 10 to the 7th squared, 10 to the 14th or something like that. But that's what we have to take account of to some extent. Okay, now in the Lorentz collision model, you don't allow the background to move. Makes the math simpler. However, that's not the math we need, truthfully. So if you redo that scattering momentum impulse from one particle passing to another, passing past another, and you allow the background particles to be moving themselves, and so forth, then you end up with the frictional drag and velocity diffusion Fokker-Planck coefficients, they'll turn out to be, they're given by some funny integrals here in terms of some functions which are called the Rosenbluth potentials after a paper by Rosenbluth, McDonald, and Judd in the late 70s, having to do with calculating the effects, these Coulomb collisional effects. And if you look at these various equations, you can see that the frictional drag is the velocity derivative of a potential, which is this equation in velocity space. This looks like Poisson's equation if it was in real space, right? There's some source and there's a del squared in velocity space. So what this equation tells us, and that up there, is that the frictional drag says drag these particles, these test particles, down to the velocity of the background particles that I'm colliding with. And then the other one, the second derivative one, is also governed by a Poisson-like equation. And you look at that and you say, well, that says keep it spread by so much. And what it does, that part tries to spread in velocity space the distribution function away from zero and keep it at some thermal velocity. So anyway, and then you do this for, I was calculating for species S test particles with species S prime background particles, and you sum over all types of background particles. Now, then that was the microscopic view. Then you say, well, really, that was only for one particle, one test particle, what it feels. But we can say, well, look, the distribution, I got a whole distribution of particles. And so I'll just say that the background has some Maxwellian distribution. You can go and calculate these Maxwell integrals, and you can find the velocity of a particle is being slowed down with a nu sub p or nu sub momentum or nu sub s. Some people call it the slowing down frequency. And this is the test particle dynamical friction. Okay, and this is the dynamical diffusion, which is perpendicular diffusion and actually a little bit of parallel diffusion in the direction that the particle is moving, because it sometimes collides with particles moving faster than it or whatever. And there's a reference collision rate. Now, so this is kind of general type stuff. And then it turns out, of course, that a plasma has electrons and it has ions. And so we have to ask about electron-electron collisions, electron-ion collisions, ion-ion collisions, ion-electron collisions, and so forth. So it turns out that you go through all that math and you can say, well, there's a momentum loss frequency, there's a perpendicular pitch angle diffusion, parallel speed diffusion, a speed reduction, and an energy loss. A subtlety, by the way, that's kind of interesting to me is that the energy loss is one form, but the speed loss is different. Why is that? Usually, you know, the speed, half the energy type of thing. Well, remember, what we're sort of doing is we got particles almost on a constant energy sphere. And so when I'm losing momentum of this directed momentum, you'd say, well, I'm just losing energy as well. But because we have speed or energy diffusion perpendicular to that, which is itself dependent on the speed. So when I slow a little bit, it changes things. So therefore, you end up with this new parallel. So in other words, nu sub v is not, the speed loss is not just half the energy loss, if energy is half mv squared, but rather there's effects due to the speed scattering away from that. All these details are somewhat important. That's what I want to try to get across to you. Now, what I meant to say, then I forgot about this slide. On the next slide, to show you, what happens? I start out with a delta function distribution function here, and I ask, what's the probability distribution as a function of time? So if I start out with a delta function, or here a little bit of thing, I go mostly on a constant energy sphere. My new perp is scattering away from that direction. And, you know, just geometrically, you can see I pass a bunch of particles, and I'm just diffusing in that direction. But sometimes I go with more and less energetic particles, so I scatter up and down a little bit. And I lose directed momentum, nu s or nu p, here, because as I scatter on a constant energy sphere, I'm actually losing a little bit of momentum. But the dominant scattering is perpendicular at nearly a constant speed, and speed diffusion is less, but it does spread the distribution function a little bit above the initial speed. And the momentum loss is mostly nu perp. Now I'll finally get to the slide I was thinking of and trying to tell you about. So then you can ask, okay, so I've got all these important momentum loss, perpendicular diffusion, speed reduction, and energy loss. And you can ask, what about if I had electron-ion collisions versus electron-electron collisions versus ion-ion collisions versus ion-electron? Ion-electron's a big hunking ion moving along, trying to push lightweight electrons out of the way. Not much energy exchange, okay? So that's what we see. So if you look here, and these are all referenced to the same reference electron-ion collision time. So we got a bunch of things that are order unity here, okay? Z is the charge of the ion. And those are all electron processes, okay? So all these processes happen on the electrons. Electron collisions, electron-ion collisions. However, ion-ion collisions, ions are moving slower by the thermal speed. Their thermal speed is square root of mass ratio, 60 times less. So they're here in this line, okay? And finally, again, ions trying to exchange energy with lightweight electrons, pushing them out of the way, so to speak, are a mass ratio 3,600 times weaker. So you got electron collision times, ion collision times, and ion-electron collision times for energy exchange, actually. And again, roughly speaking, we have, let's see, nope, that wasn't the one. I guess it's over there. Anyway, we need to be out here on these, and we need to realize that the electron collision time is different time scale collision rate than the ions. So these characteristic collision times are very different. 200 microseconds, 34 milliseconds, electron-ion energy equilibration, like 500 milliseconds. And we want to go out to 6 seconds or so. So all that needs to be taken into account, and plasma can have a response on time scales shorter than this, intermediate, longer than this, and even longer than that. And so we've got to, in principle, keep track of all this stuff. Okay, now, oh, actually, this is that. So previously, I've been talking about single particle effects. A test particle, what is it feeling? But now I can integrate over a total Maxwellian that's actually flowing with some flow velocity, and you just work through all the mathematics, and you get, again, this nu E, which is the number I'm quoting over here. And similarly, for the temperature equilibration, I've got a Maxwellian of electrons at 10 kilovolts and colliding with a Maxwellian of deuterium ions at 12 kilovolts or something. At what rate do they equilibrate? And the answer, again, for ITER is half a second or so. So these are the kinds of things one needs to worry about. Let me put it that way. We will need to go all through these timescales, and we'll have different types of models that will be applicable. So now, so that's how a single particle moves around, okay? Now what we would like to construct is one plasma kinetic equation from which we will essentially drive everything else. To do that, we would like to follow an individual particle as it moves along. How do we do that? Well, there's a formalism called the Klementovich equation. And for that, what you say is you say, well, let's make a distribution function which is a sum over all the particles of any given species, 10 to the 23rd in ITER, of the particles on particles are delta functions. Oh, why are they delta functions? Well, again, the force field for nuclear collisions is 10 to the minus 14 meters or something like that. And, you know, all these dimensions here are longer than that. So the particles, for all intentional purposes, are delta functions. And they're delta functions, they have one velocity. So so I'm going to call, well, anyway, so these, a given particle will have a given orbit, xi dt. dx dt is its velocity, mass times velocity, dv dt, Newton's equation, second equation. Force, what's the microscopic force? Well, the microscopic force is the Coulomb potential around each particle, and then a velocity of that particle crossed into maybe a microscopic magnetic field. Pragmatically, this is usually, you know, relativistically, since we're not treating relativistic particles here, this is down by V over C compared to that, so we won't have to worry about it. But in principle, we have Gauss's law, divergence of E equals charge density. Again, microscopic. All these charged particles around jiggling me. Then if you ask, well, I've got this microscopic distribution function, what's its time derivative? Well, it obeys the Liouville equation. So df mu dt plus v dot df dA plus f mu df d mu. Df mu dv equals 0. Well, so that is a Liouville equation, and these particles would just map along, and et cetera, et cetera. However, if we average that over a small phase space volume, which is of the order of the Debye length, or a little smaller, whatever, a little smaller than the Debye length, then we can say, well, the distribution function, if we average this by saying that the average distribution function is you know, average here. Where do I have that? Oh, I don't. Anyway, the macroscopic, that we change this part, all of this, into its average, but then we have a microscopic force field dot df dv, df microscopic dv. So in some sense, that's the microscopic electric field operating on the df dv microscopic. Now here, the macroscopic force field is the Lorentz force, or if I'm in inertial confinement fusion, I put in a plus a, what do you call it, compressional ablation force, but anyway, or gravity if I'm in astrophysical applications. But in magnetic plasma, magnetic fusion, we just have the electric field in V cross B. So this is then our kinetic equation. It becomes macroscopic, means anything larger than a Debye sphere. And remember, Debye shielding cuts off interactions. Equal to the total time rate of change of that macroscopic, longer than Debye length scale lengths, is equal to the microscopic stuff, which is going on within a Debye length. And that's our Fokker-Planck coefficients that we derived on the last sequence of slides. It's the velocity space scattering. And that's local. So remember, this whole schema here is taking a place in like 10 to the minus 4 meters. And so this collision operator that we're going to get on the next slide, a Fokker-Planck collision operator, is scattering in velocity space localized to 10 to the minus 4 meters. So it's really very, very local. So that's what we're going to talk about on the next one. It's the two-particle correlation function, it turns out, with cumulative small angle scattering from all the stuff going on within 1 debye length, which is that log lambda effect. So then putting this together and making that into a collision operator, we will have that the total time derivative of macroscopic, anything larger than a debye length, is equal to just the total time derivative, you know, it's df dt plus v dx dt, df dx plus the force, Lorentz force field df dv is equal to collision operator. And now I introduce something else. I will use the symbol collision operator. By the way, my notation is always that these curly brackets, well, first, the C is a math cal in LaTeX. It's calligraphy language or whatever. It's a script C, okay? And I mean that to be an operator. We'll talk about that. And the curly brackets mean operator on, in this case, the distribution function of the species I'm interested in. And I'll have to have one of these equations for each species, okay? And then we ought to introduce another S here. If nothing else, we'd like some fusion collisions. And how are we going to treat fusion collisions? Well, they're rare. We'll use a Boltzmann collision operator because they're a nuclear collision process, DT fusion. But also I might have, and I've tried to write just to remind you as we go along here, we might have sources and sinks of heating. We might have radiation. We might have at the edge of the plasma a little neutral recycling, so we get some neutrals to go out the wall and come back. The very edge, outer few centimeters of the plasma. Excuse me. So this is going to be our fundamental equation that everything starts from. That source term at the last there is, however, only applicable out on the energy confinement timescales, roughly speaking. So that's out on the seconds timescales. We're going to have a lot more stuff, as I've indicated up here above, ideal MHD processes, extended MHD, transport, before I get to that. Let's put it that way. Okay, so how do we develop that Coulomb collision operator? Well, the easiest way is we use what's called the Fokker-Planck description. And the basic idea is you imagine that there are these little kicks, delta V, delta T, which we calculated, those little momentum impulses per unit. I put in a delta T to make them, what do you call it, dimensionally correct. But anyway, a lot of people don't put in the delta T. Anyway, and this was our dynamical friction, and this was our dynamical diffusion. And you can show, it turns out, that this Fokker-Planck description, this equation up here, is actually the small momentum transfer limit of the Boltzmann collision operator. Boltzmann's still great. It's just, and Boltzmann collision operator is, of course, an integral differential equation, but really integral equation. But if you make the small momentum transfer for any given collision, or the collisions taken into consideration in moving 1 debye length in 1 plasma period, or a picosecond, then you take that small momentum transfer limit, small momentum transfer compared to your current velocity, momentum, or energy, then you get this Fokker-Planck description out of the Boltzmann collision operator. Now, what I talked about earlier was this electron test particle hitting background immobile ions. It's called the Lorentz collision model. And that just scatters at constant energy, okay, scattered on a constant energy sphere. And so that turns out to be just collision operators, nu of v, times in spherical velocity space coordinates with the axis in the direction of the velocity v. It's in spherical velocity coordinates, it's just this, which we're used to seeing in many regards. Again, this Fokker-Planck collision operator is local in space to within a Debye length. So as long as you're longer than a Debye length, and everything we're really going to care about is longer than a Debye length, this is local in velocity space. It is, however, a second order in velocity space derivative. And that's, to me, rather important because, as I'll talk about on the next slide, I think, what it's going to cause is it's going to cause the distribution, the plasma kinetic equation to be a parabolic differential equation, not a first order hyperbolic equation. So let's take a look at, so let me just briefly, I got to go back to one other thing. So there's various ways of writing the Coulomb collision operator. And depending upon what you're doing, want to make analytic proofs, you want to have something you can evaluate on a computer, or you want to have something that you can get some intuitive physical feel out of. There are various ways of writing the Coulomb collision operator. So the first, up above, indicates it's a divergence in velocity space. So if you take integrals over velocity space, you're going to be able to convert a divergence in velocity space into a surface integral at infinity, eliminate a bunch of terms. That's very helpful. This Fokker-Planck operator is in this form, the divergence of this stuff. And here you really see the dynamical friction and the diffusion in velocity space. If you have distribution functions of background particles which are not Maxwellian, then you need to use what's called the Rosenbluth potentials that I mentioned. They have their own equations and so forth. Those are somewhat complicated, and I won't be using those very much. Finally, another form that's very useful is the so-called Landau form, and I might, which is given here. Again, it's a divergence in velocity space, but you know, it's a slightly different form. This one you can kind of feel, hey, this is kind of similar to the small momentum transfer limit of the Boltzmann equation. Historically, Landau derived this Landau form of the collision operator, as I recall, back in the 30s, 40s. Rosenbluth, McDonald, and Judd did this Fokker-Planck description, basically following on Chandrasekhar's approach to stellar dynamics, the statistics of stellar dynamics. And for a long time, they were thought to be somebody's wrong or, or different. But later, in about the 50s, people, late 60s and early 60s, people figured out, oh, you can just go from one to the other. They're really the same. It's just that they look different to you. Now, again, when we start out, we're going to start on a fast time scale, treating many fast time scales. But over some period of time, when we get longer than a collision time, then we say, look, the distribution function is forced to a Maxwellian. When it's forced to a Maxwellian, then, you know, maybe I ought to expand the collision operator in terms of a Maxwellian plus a correction. And that's how we will get fluid equations beginning next time, actually. But what we do is we say the collision operator between one species of test particles and one species S prime of background particles, which includes the same as the test particles, will be a Maxwellian of the two Maxwellians colliding plus the linearized collision operator operating on the perturbation of the operating on the test particle perturbation. And then this linearized collision operator is what we will call, was often called a test particle operator. So it's the deviation from a Maxwellian colliding with a Maxwellian species. But and that will be important for short time scale processes, namely those up here that are in this range before the collision time. On the other hand, when you get out to the collision time, and even somewhat before that, you also have, in a rigorous form, collisions of the background perturbed the Maxwellian of the background with that perturbed distribution of test particles. And this is called the field particle part of the operator. What does that do? In the Lorentz collision model, you have the plasmas moving along, and the Lorentz collision model says you scatter it in velocity space, you lose a little bit of momentum. Where did that momentum go? Well, truthfully, where it went is it moved the background a little bit. So that's the field part of the operator. This, it says, is the background actually collides with the test particle group of particles. And so you have to have both of these in order to get momentum conservation in the perturbed distribution functions. And when you do kinetic analyses, both parts are important. And anyway. So this test particle operator has some interesting forms, at least I think they're interesting, that you can write it in. Interesting in the sense that each one has its own, perhaps, meaning. So again, it's a divergence of a flow or current of particles in velocity space across boundaries and so forth. So you write it first in its Fokker-Planck divergence form. Then you say, okay, I'll make a Maxwellian background. Or I'm sorry, no, not even Maxwellian yet. But anyway, I have perpendicular scattering, I have energy loss, and I have speed diffusion. So again, perpendicular scattering, momentum loss, and speed diffusion about the energy. But then you can write it in a different form, which is detail. But you look at this and you say, well, gee, if it's the same species as S is S prime, so it's electrons colliding with background electrons, then the natural solution that gives you collision operator equals 0 is that this perturbed distribution should be e to the minus v squared over the thermal speed squared, or oh, that's a Maxwellian. So this says, hey, this is trying to cause it to be a Maxwellian. This is trying to scatter it. And then if you want to do an analysis, which I'll do at the first of next lecture, of collisional effects on Landau damping, what you would like to have is a diffusion equation in which the diffusion operator doesn't have stuff inside. It only has second coefficient and second derivatives. So then what you say is, well, oh, I've got a Lorentz scattering operator, which is this horrible thing, a speed diffusion operator, a drag operator, and a just extra term, which we don't like. But anyway, and as long as I'm short of the collision time, I don't have to care about that. Anyway, this is the test particle operator, which is going to be applicable on the short time scales compared to the collision time. The Lorentz scattering operator is written in this form, usually. This form emphasizes that it's actually, what do you call it, momentum angular scattering. You see that form in quantum mechanics often. Spherical velocity space coordinates, it looks like this, or like this, or like this. So, anyway. Now, this Coulomb collision operator, Fokker-Planck Coulomb collision operator, which is the one we have to deal with mostly. The source thing with the Boltzmann collision operator is just kind of an additive at the end type of thing. It satisfies various conservation laws. In Coulomb collisions, no particles are created or destroyed. Fusion hopefully creates and destroys, but Coulomb collisions, as you just go along on a charged particle trajectory, doesn't create or destroy any particles. So there's no density change. Momentum, what momentum you lose from one species, you gain from the other. So momentum lost from one is going into the other one. So you get momentum conservation. Likewise, energy exchange. Coulomb collisions are elastic collisions. So energy you lose from one species goes into the other species, and you have that. If you have only one species of particles, there are some special plasma cases like that, the Maxwellian is the equilibrium solution for that species. If I add extra terms, as we will, in transport calculations, then it tries to get there, but it doesn't make it. Another property is if the distribution function is initially positive definite, then it's always non-negative, okay? I'm sorry, if it was non-negative to begin with, it'll always be non-negative. Also, you can show this collision operator is Galilean invariant. You just go back and change V to V plus some motion, and it's the same. It's a bilinear vector functional, and so entropy of the whole plasma, F log F integrated over all velocity space and all real space, a la the Boltzmann H theorem basically says that for time scales long compared to the interaction time between two particles, or for electron-electron collisions, let's say, if you only had dFdt as collision operator, then the distribution function will be Maxwellian. The problem is dFdt might have some other things. Like in a tokamak, you take a charged particle, it goes from the outside of the torus around to the inside, and lo and behold, it says, wait a minute, I'm in a magnetic mirror sort of situation. I had to go to the high field side of the tokamak, and I might get reflected and be trapped and stuff like this. And so in that context, you can have, it won't make it to a Maxwellian. It'll have corrections, and those corrections will be important. Now, there's a trickiness that goes on. We know that the Boltzmann collision operator is a bilinear, what do I want to say, is a self-adjoint. And the if you make this analysis, as we will, the distribution function, when we get out to these longer time scales, like longer than collision times, and we have a small gyro radius approximation, then our distribution function is to lowest order Maxwellian plus a gyro radius small, 1 part in 10 to the 3 distortion. And you can show by going through the math that we have that the time rate of change of the entropy of that species is summed over all other species is like this. And you go through the math, and basically, since the logarithm of Maxwellian is some constants plus mv squared over 2t, and you can show that in going from that line to this line, that the density moment, because of density, momentum, and energy conservation, you get rid of some of these terms. But one of the tricky ones, it turns out, is this delta F and the collision of the Maxwellians. And I will be talking about next time Chapman-Enskog-like approaches, which are usually thought of as only valid in collisional plasmas, strongly collisional plasmas, collisions dominating. But in plasma physics, we're going to extend that, or particularly for tokamak stuff. We're going to extend that by saying, no, that's not the whole story, and we'll do a modified form of Chapman-Enskog. Chapman-Enskog has the virtue that it says to lowest order the distribution function is a Maxwellian. And then there are kinetic distortions. And those kinetic distortions, however, because you'll use the fluid moment equations to change the plasma kinetic equation into what I'll call a Chapman-Enskog kinetic equation, those kinetic distortions will then not have any density, momentum, or energy moments. As a result, this funny term, collision of Maxwellian, two Maxwellians with a delta F, if that delta F doesn't have any momentum or energy, it'll vanish. Anyway, when you can do this, you can basically show that the linearized linearized collision operator is a self-adjoint operator. And there could be an additional term if you do not use the Chapman-Enskog-like approach, but if you use, which people are worried about, it's temperature equilibration basically, extra thing. But if you use a Chapman-Enskog-like form, you won't have that trouble, and the equation is self-adjoint all by itself. Okay, final subject kind of for today. So we got this plasma kinetic equation. How do we go about solving that equation? Well, the left-hand side, and first maybe what we need to say, what do people think about it, or how do they talk about it? First comment is, these collisions were pretty weak. Remember, collision frequencies, plasma frequency, log lambda over n lambda to pi cubed. N lambda to pi cubed is 10 to the 7th. Sounds pretty small. We'll throw it away, okay? If we throw away everything on the right-hand side and put this equal to 0, we say it's the Vlasov equation. Now, and that's indicated up here, okay? What are the mathematical characteristic curves of that equation? Well, they're just determined by dx dt equals v and m dv dt equals force. And then, short of chaos or stochastic differential equations, nonlinear effects, which we'll come back to, nonlinear, heteroclinic nonlinear effects, short of that, all that happens is that each particle moves along its own trajectory, and you never get any entropy production. So the classic example of that, historically, is what's called the water bag model. I'll pick up one of these for just a second. In the water bag model, you say that you have, let's say, V and X, and you have a distribution function which is a water bag to start with. As you map it in time, the area, it's an area preserving map. The area stays the same, the shape may change, but the area stays the same, okay? And you may have it loop around and do all kinds of things, okay? So inside stays the same. In the Vlasov equation, again, barring topology changes due to strong nonlinear or chaos type things, you never fuzz the boundary. So the edges of that water bag and the area are exactly the same forever. There's no entropy production. So in particular, if I add collisions, I begin to fuzz the boundary, okay? And I definitely start getting some entropy production. Or I add chaos, I can do that under special circumstances. So the idea is that the Vlasov equation just moves forwards in time, is area preserving and so forth. When you add Coulomb collisions, you fuzz the boundary, you create boundary layers at the edges, and in particular, wherever you have that the derivative is much smaller than the collision frequency, which it would be at edges, you know, at boundaries, with some new effective being the collision frequency divided by how small a region of velocity space boundary layer you have, that will actually increase the entropy. So as a matter of kind of history, a lot of people solve what's called the perturbed plasma kinetic equation in various forms, and then we do it nonlinearly also, but anyway. So to lowest order, you say you have an isotropic Maxwellian distribution function, and then you say, well, I have that isotropic Maxwellian, and I'll add a perturbation, and then it's governed by a perturbed plasma kinetic equation. A linear operator on the perturbed distribution function is some source. The linear operator is just this thing, which is the total time derivative with the equilibrium or lowest order magnetic and electric fields, and then minus a collision operator, but anyway. And the source is the delta E df/dv type stuff, plus a nonlinear term, which I'm going to ignore here for just doing this. So how do you solve the collisionless version of this for Landau damping and a lot of problems? Well, you just say, hey, this is a first order partial differential equation in time and 6 spatial variables. I just convert it to a total time along that trajectory. And I say the distribution function is whatever it was at the initial time mapped along the whatever trajectories it has, plus an integral over time along those orbits of the source function, which is this sort of thing here. And this would be a quasi-linear type thing, but and then really you iterate and so forth, but I don't want to do that. So that's a lot of things we do in gyrokinetics, drift kinetics, all kinds of instability analyses, we tend to do that. On the other hand, if you want to calculate collisional effects, what's called neoclassical transport or collisional transport or three-dimensional magnetic field perturbation transport, you start out by saying, well, I'll get to a certain, you make a set of approximations, and then ultimately you solve a collision-dominated regime where you balance the collision operator against, say, some form of a bounce or drift of particles coming from this sort of stuff, and you've averaged it out to some time. So we tend to treat these as 2 different types of problems: collisionless, collisional. And what I've been getting onto recently, and maybe it's just my current fetish, we'll see, is, well, you know, maybe we could do better. Maybe we could have one formalism to do both. So the idea there is, imagine that, well, let me go back. So all I want to do is solve this equation here, okay? Some linear operator equals some source function. All I need is the inverse linear operator. Well, what's the inverse linear operator of any linear equation? The answer is you go off and you solve a Green's function, or a Green, I'm sorry. When I was growing up, we called it a Green's function, Green with apostrophe S. But later, we're supposed to call it a Green function, a Bessel function, Green function. So anyway, so sometimes I'll slip. Anyway, so a Green function is you take your linear operator operating on that green function is a delta function from where I am now, from where I started, and so forth, to a set of Dirac delta functions. Then what the Green function is it physically represents the distribution function response at wherever I am now in xvt from wherever I started. Green's function is the mapping to get from one to the other. And so then the distribution function becomes the integration over all possible initial velocity, initial spatial positions, and initial velocity positions for all the time from when you started to right now of that source function. What are our lowest order particle trajectories in a plasma? Well, I sort of drew them wiggly, but really they're very small. I mean, we're talking 1 part in 10 to the 3 or 10 to the 4 wiggles in any one Debye length, okay? So roughly speaking, it's just a straight line orbit. I'll make it simple, okay? So my straight line orbit is just x naught plus vt. And then we can say, well, let's just roughly try to estimate this. By the way, physicists always make the rough calculation first to try to see whether there's something worth doing. They may miss something, but at least they try to make sure it's worth doing. So you say, well, the collision operator is just an a collision frequency and a isotropic scattering operator in velocity space. If I was doing Brownian motion in real space, that would be an isotropic collision operator in real space, okay, for neutrals. Or for short times, I'll use that isotropic collision operator. Or long times, I'll use a drag operator, which is known as the Crook collision operator. And so the combined, and I can't do the whole problem, but anyway, the combined green function is then that in an infinite medium, in velocity in real space, it's just a delta function along that straight line orbit. But then it's got velocity scattering, okay, on a short time scale, or on long time scales, it's that I just drag down the whole distribution function. Now, we'll do a lot better than that with a Fokker-Planck operator, but anyway. So the idea is that this is then the propagator for particle motion. So the propagator says, I'm only moving along the field line, or along my original trajectory, but now I'm kind of scattering a little bit in velocity space. That's what that is. And remember, our collision frequencies are of the order of 10 to the minus 7 of the natural fluctuation frequencies, the fastest fluctuation frequencies in plasma. So I'll come back to this because I'm going to show you in greater detail next lecture. But anyway, I would suggest that there's a green function approach whereby you say, well, to lowest order you have these characteristics of the first order partial differential equations, either doing Lorentz force, Newton's equations, or Hamiltonian form or whatever. And then you have scattering, slow velocity space scattering of that. So next time I'll tell you about Coulomb scattering effects on linear Landau damping. This can produce for you irreversibility, temporal irreversibility, and entropy production in a plasma kinetic approximation that allows the test particle approach to be rigorous, it turns out. It can modify nonlinear trapping. If you have a particle trapped in a magnetic field or a potential, or electric potential, then if you have a little fuzz on it, well, you know, it gets a little bit funny. And so you may not be able to produce what are called BGK, Bernstein-Green-Kruskal, holes, clumps, and so forth at very low collisionality because you'll get fractional. It's a boundary layer effect in velocity space near the resonances that are involved, and so you get spreading of that. In magnetized plasmas, we actually do it in terms of energy, magnetic moment, and gyro angle. And then this green function could then produce slightly probabilistic trajectories that might limit the growth of weights in delta F codes, as they're called, for the perturbations. This is a little beyond the level here, but anyway. And it includes, it introduces an effective collision frequency, which is the collision frequency times K per rho. So wavelengths shorter than the gyro radii will be actually averaged a bit more in gyrokinetics. And in tokamak plasmas, there's some details here about K perp and K parallel. Okay, so this I've been trying to give you a lot of flavor for what goes into, on a microscopic level, the Coulomb collision operator, how it involves the statistics of interactions with of the order of n lambda Debye cubed 10 to the 7th particles within a Debye sphere. So you get some statistics out of that. And so then what we've been describing is the scattering of the test particles' velocity in perpendicular parallel diffusion, momentum, and energy exchanges. Electron and ion collision frequencies are very different by, again, square root of mass ratio, factors of 60 from the electrons to the ions to ion electron. This Fokker-Planck operator is, we're going to use it later as we get into the fluid moment approach, which we'll get to next time. And tried to tell you how all this kind of fits into a plasma kinetic equation, which is, again, this thing over here. And this is actually a fairly well-developed area in plasma physics, fusion, magnetic fusion plasma physics, although I would say not always well appreciated, all these things. And to me, this green function solution, often the plasma kinetic equation is solved in more or less collisional or collisional limits, collisionless or collisional, and using a 6-dimensional x and v Green's function allows you to include both types of effects, and I think it'd be useful. A open area, which I think is still not very well described, is when you have a non-Maxwellian background. Why would you have a non-Maxwellian background? One of the ways you heat a tokamak plasma is by what's called an energetic neutral beam. So you arrange to do some technology whereby you're able to produce, in D3D, 80 kilovolt neutrals, which can then get across the magnetic field, and they get either charge exchange collisions with ions, or they get ionized in the plasma. And in the process, what you do is you say, I've got a 3 kilovolt average ion temperature, and I exchange with an 80 kilovolt ion, a neutral that's come in that then becomes an ion by the ionization process. Or by charge exchange, you just switch for the electron from one to the other. And then this fast ion, you got a 3 kilovolt background plasma, 80 kilovolt injected ions effectively. They came in as neutrals, they got ionized. And it slows down by Coulomb collisions. And we calculate all that out, and more or less it turns out that in tokamak plasmas there is most of the time, almost all the time, there's just collisional slowing down. That's all great, and we do the analysis. I had a lot of fun on this a long time ago. And what we say is, oh, I got an 80 kilovolt plasma energetic beam, and I got a 3 kilovolt plasma. It's just an extra species that I can kind of add in extra. So then they were doing experiments on TFTR, and actually on D3D. And it turns out that when you create these neutral beams, a technical difficulty is you start out with 80 kilovolts, but the way you produce it is by, you do ions, you accelerate them to through a chamber to 80 kilovolts, and then you put them through a charge exchange neutralization area and convert it into neutrals and send them into the plasma. That's fine if you start out with deuterium. Deuterium plus you accelerate and so forth. Suppose you start out with D3, that is to say, a triply charged deuterium chunk. Okay, 3 deuterium nuclei together, it turns out. Well, 1 with 2 electrons. So anyway, you get a situation where you're accelerating 3 times the mass with the same amount of potential. Lo and behold, you get, instead of a 80 kilovolt particle out the back end, you get 80 kilovolts divided by 30. And then you have the situation that, suppose you do have a 10 kilovolt plasma. 3 halves T is 15 kilovolts. And suppose you got some tail particles, a little bit above 15 kilovolts. 80 divided by 3 is, what, 23 kilovolts, okay? Or 26 kilovolts. That's not much above the background. So we have the problem that we do it as a separate analysis, a Maxwellian background and a high energy tail. But when the high energy tail's only, a little bit above the background, or actually we had a situation on TFTR where they had a 120 kilovolt injection and the plasma was over 40 kilovolts. And so we were injecting that 1/3 energy component was actually going in below 3/2 T of the plasma. Well, I had various experimental colleagues who came to me and said, well, what do we do now? And my answer, of course, was, don't do that. We don't have an answer is the basic thing I would say. But anyway. Okay, so let me just finish by saying, what are we going to cover next time? So next time I want to start with a discussion of a kinetic solution of Coulomb collisional effects on linear Landau damping, something just published recently. Then I really want to get into plasma fluid moment equations, but we needed this introduction, it seems to me, of the Coulomb collision operator because we're going to have to go longer than the collision time and get those things right. So we'll talk about fluid moment equations and what closures we need, expanded, how we do extensions of grad 13 moment approximation, turns out, and Chapman-Enskog-like equations and closures for an unmagnetized plasma, and then what we do for magnetized plasma. And then lecture 3 will be, this will be general magnetic equations, giving us Brzezinski fluid equations. Then we'll specialize to tokamak plasmas, and finally, the Friday, we'll talk about some specific tokamak modeling things. And just one final comment, if you look in detail at my lecture notes, the detailed ones, they only got about halfway through. I ran out of time, as you'll see, but I hope actually after this to finish that for other reasons. I'd like to be able to do that. And the lectures, so the first 2 lectures are relatively comprehensive. The last 2 will be more referring to open literature and trying to summarize that. So anyway. Thank you for your attention. I'll be glad to answer questions.